Log on, tune in, find out. Another good idea from Cambridge.
Okay, so before I want to erase it again, I think I should quickly go through this notation. So I want to remind you that last time, and I think everybody who's supposed to see it saw it. Now, so I'll probably just, where's the switch? Okay, that's the best I can do. So we are going to work over the ground field F, which is algebraically closed of arbitrary characteristic. We are going to fix once and for all a parameter xi, which is non-zero element. And you should think about it as a Q in Hecke algebra, but Q will play a different role, so I call it xi. Then from this xi, we define this number E, which is sort of characteristic, which I refer to a quantum characteristic. If xi is 1, for example, it is indeed a characteristic. And from this E, and therefore only from F and xi, we determine a Lie type, which I denote gamma. It's a little bit more than a Lie type. For the purpose of this theorem, I need to fix an orientation, although I could do it for other orientations also. So this Lie type depends on E. And then there are all the usual bells and whistles which come with Dünchen diagram. There is, first of all, the vertex set, which I denote I, in which in all of these cases can be identified with Z mod EZ. Aij Cartan matrix, normalized form, Kac-Moody algebra, fundamental dominant weight, sometimes denoted omega I, but I denote it lambda I following Katz. Simple roots alpha I, fundamental, the set of dominant weights, positive radical lattice or whatever it's called, non-negative linear combinations of alpha i's. And then using this Lie theoretic data in a sort of, for now, slightly artificial way, just as a bunch of placeholders, we were able to define a class of algebras, HD lambda, which in general can be obtained as a quotient of the affine Hecke algebra, or degenerate affine Hecke algebra, depending on whether xi is 1 or is not, and we cover both cases, by the corresponding relations where we just prescribe the eigenvalues, informally speaking, and the sizes of the possible Jordan blocks for the action of the element xy. And so this is just a placeholder. You see, basically here I just need a number ai. But I want to think about this number ai in terms of this Lie theory, which is a little bit artificial, as I said, and silly even at this stage. And I want to remind you that nu of I denotes I if xi is 1, and q to the I, if xi to the I, if xi is not 1. And this can be considered as an element of the ground field in an obvious way. So a special case when you take just very special dominant weight, namely the fundamental dominant weight lambda 0, you recover kind of this most classical of all situations where H, the cyclotomic Hecke algebra, is the Hecke algebra of the symmetry group. When xi is 1, it's just the group algebra of the symmetry group. And, so if you, for example, just want to listen to this talk for the group algebra for the symmetry groups, you can do it by specializing lambda to lambda 0 and xi to 1. So this case is definitely covered. So what else? Okay, so yes. So one small remark which I wanted to make in reaction to Arun's comment today, that complex reflection groups will play an important role in the next week, but they didn't appear this week, or almost did not appear. Actually, this Hecke algebra is a Hecke algebra of a complex reflection group in general, properly understood. I won't go into that because for me it's much more smooth to just introduce them as this family, but actually it's a family of complex reflection groups for which it is corresponding Hecke algebra, sometimes also called Hecke algebra. And these algebras were defined independently by Hecke, Breuer, Malle, and too unique as far as I know. Okay, so so this is the objects we want, whose representation theory we want to study, and I claim that if you want to study their representation theory, you should consider them not from this point of view. This is a presentation by generators and relations, because a fine Hecke algebra is given by presentations by generators and relations, and this is an extra relation. But I claim that instead you should consider a different presentation. And this is a presentation which is written on the blackboard, copied from the last time, with just one minor difference, that last time I missed one relation, which is now framed. So you should add it. It's how to commute psi's and e's. I forgot about that. So we discovered this this presentation with John Brandon by reading a paper by Khovanov and Lauda, a recent paper, and we just discovered it recently. And basically, what happens is that Khovanov and Lauda, they define a family of algebras, which were also independently defined a little bit later by Rukia, but independently. So this class of algebras, which they defined as some sort of diagram algebras in terms of pictures. But in type A, what they do is, and by type A I mean this or this type. So in this type, what they do, they write down exactly this presentation, except for one final relation, which I forgot to write. See, this is still independent of lambda. So, but actually, it's good that I forgot to write it, because this is what Khovanov and Lauda consider. So this is sort of a fine Khovanov-Lauda-Rukia algebra. But if you also add a cyclotomic relation, just like this one, which takes a slightly different form, and I'll put it in. So this extra cyclotomic relation, you get cyclotomic Khovanov-Lauda-Rukia algebras. No, you don't. So on the affine level, they don't agree, but on the cyclotomic level, they do. Although on the affine level, they do agree up to some completion, according to Rukia. Okay, so
this cyclotomic relation just allows you to go to completion.
Yes. You can say it this way, but it allows many other things also. Somehow it's the right quotients. It's the right finite dimensional quotients. But in particular, what you say is true. So y1 to the power lambda alpha I1 on the idempotent E of I is equal to 0. If you think about it, it's really the counterpart of this relation. You see, now, if you remember a little bit about how I defined those y's last time, and e's and psi's, although I didn't tell you much about psi's, but e's are sort of weight idempotents. They are the idempotents which project to a particular weight space. And y's are made out of x's, out of JM elements, by subtracting an appropriate eigenvalue, so that they become nilpotent. So, and if you take that into account and you think about this and that, you will see that the two relations correspond, basically. Okay, but at any rate, so this is a theorem. And so my first remark is that this theorem shows that HD lambda is a special case of, strictly speaking, cyclotomic Khovanov-Lauda-Rukia algebras when instead of an arbitrary quiver, you consider this cyclical linear quiver. Okay, so it's kind of interesting from that point of view, because it connects it to these other algebras, which you know presumably arise from some other considerations, in particular certain diagram algebras for Khovanov and Lauda. Okay, so my second remark is what I have already done last time, and I think it's perhaps the most important thing, is that this presentation is manifestly homogeneous with respect to an obvious grading. And so we can define, so this presentation makes HD lambda into a Z-graded algebra. And this is a kind of Z gradient which is very well hidden because it's extremely difficult to see what it is in terms of the usual generators. So it's all hidden into this isomorphism. Once you believe in the isomorphism, you can work with this algebra in this presentation. And the degrees that you prescribe are for the idempotents, you prescribe degree 0. For the y's, you prescribe degree 2. And for the psi's, on the idempotent E of I, you prescribe degree minus AIR, IR plus 1 Cartan number. And please note, I also made a misprint in that place because I was trying to be nice and explain what it is. And so you should never be nice. So this is the correct formula. And so then the presentation is homogeneous. And so this makes HD lambda into a graded algebra. And so you can go back to all your classical problems, which you might have liked or might not have liked, but usually people like, say, representation theory of symmetric groups. And you can say, okay, we've been missing something because we've been studying representation theory, but we should have been studying graded representation theory, and it presumably will produce more information. And I also made the remark that you actually do not lose any information in doing this, because by general principles, every finite dimensional module over Z-graded algebra is gradable. And in fact, in a unique way up to a shift of degrees. It's a general nonsense fact, and therefore, you don't lose information. You are considering all simple modules, but you now try to get more information by understanding what grading is for. And by now, there is enough evidence that this is, who knows, maybe this is a silly grading, but by now there is enough evidence, and I will try to convince you that this is the right grading and that it corresponds to all the right things. In particular, in the picture of categorification, if you use usual representation theory, you just categorify Kac-Moody algebra. If you use graded representation theory, you categorify quantum group. So that's enough evidence that this is the right grading. Okay, so but I want to make some more remarks concerning this presentation. We haven't stared long enough in this. So if you will be asking some questions about this presentation, I will usually just stare at you kind of puzzled, and you'll think, oh, why doesn't it sound like a contradiction or something? Like yesterday, there was a question which I still can't quite answer actually. But please keep doing this, because like I said, we haven't stared at this grading long enough. And for yesterday, Meinhof explained to me that this grading solves a conjecture from Andrew Matz's book, for example, which I have no idea about. So if you stare long enough at this new presentation, you might see solutions maybe to some of your favorite problems. But because I claim that this isomorphism is actually rather non-trivial. A lot is buried into it. But anyway, so let me show you some things. So the next remark is that this grading is very nice because it's extremely well adapted to block decomposition. So you see, usually when you have a group algebra, to decompose it into blocks, into two-sided ideals where you cannot decompose any further, it's a hard thing, right? And then even if you know how to do this kind of in theory, and you have a presentation for the big algebra, there are no general procedures for getting a presentation for a block, right? So you have presentation for the group algebra of symmetric group, Cox representation. Give me a presentation for a block. There's no way, it doesn't follow there's no connection. Okay, but this presentation is perfectly suited for that, and you can decompose into blocks very, very nicely, and you can get a presentation which is just induced by this presentation for each individual block. So let me explain you how this is being done. Okay, so this is remark 3. So this presentation turns out to be well adapted to a block decomposition of our algebra. And in fact, again, I'm going to do this block decomposition. I could do it in various ways, using abaci or coarse and all this usual combinatorial stuff. But the nicest way to do it is using Lie theory notation again. And it comes extremely smooth. So all I have to do is this. I have to fix, so if we deal with HD lambda, then I have this D. And for this D, I'm going to fix an element of Q plus of height D, so that the sum of coefficients is D. So to deal with HD lambda, fix an alpha in Q plus of height d. And now let's define an idempotent E alpha to be the sum of all idempotents EI, where I runs not through all d tuples, but through the d tuples which the set of d tuples which I want to denote E upper alpha, where I upper alpha, where I upper alpha is the set of all d tuples such that alpha I1 plus dot 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 plus I alpha I d is equal to my fixed alpha. Is this okay? So alpha is fixed. This is a tuple with entries I1 through ID. And I insist that the sum of them is alpha. But of course, this is a too fancy way of saying that I'm just taking an orbit of the symmetric group as D, which acts by permutations on tuples. Because these are what the orbits look like precisely. Because it's just the content. It's how many of those I1s, I2s, and so on, IDs I have. It tells me what the SD orbit is up to permutation. And because they're linearly independent, this is a fancy way of fixing an orbit. Okay? So basically what I'm doing is I'm just choosing an SD orbit up to permutation. I choose all such tuples which belong to this. What could be easier than that? And the claim is, and this is actually proved in full generality for any type already in Havanov-Lauda paper, that for any field, this is a primitive central idempotence. There is one caveat, the usual caveat, or 0. So remember, we still don't know which of those E sub i's happen to be 0 as some non-trivial consequence of these relations. And so in principle, you can only figure it out once you start doing representation theory. And so also these might correspond to no blocks, because they might just all be 0. Maybe there are no such weights, and then you're doing nothing here. Okay, but you just take all the non-zero ones, and then correspondingly, you can define the algebra E alpha H d lambda, which I will just simply denote usually H alpha lambda. And then it's either 0 or it is a block of H d lambda. And in fact, for this block, we can write down the presentation by generators and relations in exactly the same way. And so this now, this H alpha lambda can be presented exactly as in theorem 1 in the theorem above. And the only change which you should ever make is now you don't consider all d tuples, but you only consider d tuples from a fixed for a fixed alpha. With the only change everywhere that instead of I to the d, you just consider one orbit I to the alpha. And otherwise, it's all the same relations. Is this okay? And in particular, a block is also graded. So, in particular, we can work separately with blocks. Each block is also graded. And in fact, what happened was that Havanov-Lauda actually defined already these algebras. They already did it for the blocks right away. Okay. Some other comments. Again, going back to the comment which I have already made last time. The most amazing for me feature of this presentation is that it doesn't have xi in it. And in fact, at first it looks like there's a mistake somewhere. So let's remember that 5. There is no xi in theorem above. And so xi actually does not show up in these relations, although it of course does show up in these relations. But it shows up rather indirectly, because xi only tells us what E is, and therefore xi tells us what Lie type is. And through this Lie type, xi actually does come in. But you see, because it comes in so indirectly, whenever I have two different xi's with the same Lie type, I should get the same algebra, provided the field is also the same. And then this trivial observation actually, on the nose, at least as far as we were able to see today with Meinhof, seems to settle the following question, the following conjecture from Andrew Matha's book. So the issue is that you could have Hecke algebra with two different Q's. Okay, and those two different Q's, you know, if they are two different primitive roots of unity of IC, then they might be connected by Galois automorphism, but in general they might not be connected by Galois automorphism. And then you really don't have any tools to establish that decomposition matrices are the same, for example. So if you have two Hecke algebras with different Q's, Q and Q prime, but if E is the same for those Q's and the ground field is the same, then the conjecture is that decomposition matrices are the same. Of course, they are the same because the two algebras are isomorphic. It's much better than that, right? So basically, since xi, there is no xi in these relations, and so if Lie type is the same, and the ground field, of course, is the same. Otherwise, I cannot do isomorphism of algebras. Then our Hecke algebras are isomorphic. And so, since Meinhof only told me this an hour ago, I didn't have a chance to think more about it. But I think it seems, yes. Well, the conjecture is that the decomposition matrix depends only on E and P. Yeah, but the presentation is the same. So whenever it follows for the presentation that there is 0, it will follow in all cases. Okay, so you scared me a little bit, but I think I'm fine. But I mean, it is to be checked. I mean, like I said. Okay, but let me point out some other curious thing, a special case of this sort of observation. Yes. Yes, but these relations are defining relations. So whichever EIs are 0 should follow from these relations, right? And if relations are the same, then the same EIs will be 0. Am I missing something? You think? Well, in order to construct an isomorphism, I defined EI. Okay, and of course, if you have two different Hecke algebras, EIs might be different. So you know, we go through we get isomorphism going via this algebra defined by generation in relations. So I'm not claiming that E of I will be the same in those two algebras with two different Q's and Q primes. In fact, they won't be. They couldn't be because they're two different algebras, right? But they are identified via this isomorphism. I hope it's okay, but it might be that I'm missing something silly. Okay, so but let me consider a special case of that, which I actually have seen, you know, and I thought that already was quite surprising. So let's consider the situation where characteristic of the ground field is 0 and Q is generic. That is not a root of unity. Thank you. Yes. So then you see it could be 1, or it could be not 1. And of course, in this case, we always just get type A infinity. Right? right? And so the algebra is the same algebra. The ground field is fixed. And so it shows that the Hecke algebra is isomorphic to the degenerate Hecke algebra. Now in level 1, this follows from T's deformation because both algebras are semi-simple in this situation. But in higher levels, these algebras are not semi-simple. And I think it's already quite surprising that in the generic situation, the cyclotomic Hecke algebra is isomorphic to its rational degeneration, what's called, although I never knew what these words meant. But so this degenerate and non-degenerate Hecke algebras on the cyclotomic level actually are isomorphic. So this is something which Aaron thought was not surprising because on the affine level up to completion, this is precisely what Lustig proves. But this is done as an isomorphism without completion, so it's still quite nice, I think. Both algebras are finite dimensional. Okay, and then one final remark about this presentation, just to let you know everything we were able to notice about it so far. Even if the field is not, I mean, even not in this generic situation. Now let's consider non-generic situation. And in fact, let's consider the situation where the fields are different. I want to consider, to be more precise, now the situation of two different fields. That's the only time in my talk, so I'll have to use another letter for another field. So F will be this field. Let's say it's a field of characteristic P. So the next situation, characteristic of the ground field is P, positive. And let me consider another field, K, of characteristic 0. And in this situation, let us take psi to be 1. And in this situation, let us take psi to be pth root of unity. Okay, so I have positive characteristic psi is 1. For example, this is modular group algebra of the symmetric group in level 1 for lambda 0. And this is a Hecke algebra at root of unity, but over field of characteristics 0. Okay, so these are these two cases which traditionally people know are quite comparable. They look like each other, but this case is easier than that case. In fact, people sort of more or less understood this case, but this case is still a mystery. And the idea is to somehow try to go from this case to that case, but it's not so easy. For example, we saw that in Meinhof talk, you sort of have to specialize in two different ways to go like that. Okay, but at least we can observe that in both cases, of course, E is P, and therefore the Lie type is the same. So what these two algebras are, one is Hecke algebra at root of unity, the other is just the degenerate case at characteristic P. These are the same algebra but over different fields. And in fact, what you can do, you can consider a Z algebra, which is, or just subring, generated by these generators inside of the characteristic 0 algebra. And then if you extend scalars to K, you get the characteristic 0 root of unity algebra. If you extend scalars to F, you get modular group algebra. If you want. Is this okay? It's a little bit confusing, but what I'm saying is that this relation between root of unity case at characteristic 0 and characteristic P case becomes really straightforward reduction modulo P and nothing else, totally in spirit of Brouwer-Nesbitt. And I want to write it down because I actually believe this is quite an important thing. So I'll have to choose some notation perhaps. So let me say, I don't know, let's denote by H dz lambda to be the subalgebra, the Z subalgebra of H d k lambda. I'll have to remember the field now, generated by our generators, generated by E's, Y's, and Psi's. Okay, so then one can check, and this is quite easy, that if I start with this algebra, and you see I don't have to specialize psi to anything because there is no psi left. So all I'm doing is I'm just tensoring with F, and I claim I'll get my HDF. Or if I'm tensoring with K, I'll get my algebra over K. And so from this point of view, it is extremely easy, well, in theory, to go from root of unity case to characteristic P case. All you do is you start from characteristic 0 module. You choose an HDZ invariant lattice, just like in usual modular representation theory, like in Brouwer and Nesbit theory. Take any vector, multiply by this, you'll get a lattice. And then you reduce all entries modulo P, and you get a module over this, characteristic P. So this relation is very clear relation, and it's precisely reduction modulo P relation. Is that okay? Excuse me? This is actually a subtle issue, and I suspect that I believe the question is it true that this algebra, which is generated by these guys, is given by these relations? And actually, I don't think it follows. But there is no basis theorem for the cyclotomic algebra. It might follow, and I think actually it's true, but I think this subtle issue is not settled. At least as far as I remember, we can't do it. And I think indeed the issue is about the torsion. But nevertheless, you can still reduce modulo P. I mean, of course, there is no torsion in this algebra. but whether it's generated by by those relations only or not, I think it's open. Well, but that should be the case. It might actually be very important too. Okay, so now I can state again, following Meinhof, also I can state James conjecture again. I mean, what James conjecture says is that this reduction modulo P is doing nothing. You take a reducible module at root of unity, you reduce modulo P, it's still irreducible. Okay, of course it's not always true, as we know, but it's true in the James region. And I will tell you what this region is a little bit later, because it's nicer to do it using Lie theory. So if once I have an irreducible module with highest weight lambda, I will be able to tell you very nicely what the James region is. So, but right now I can already spell it out, because I sort of also, just like Meinhof, I hope that maybe discussion of this problem will become one of the main themes of this conference. One can even dream that maybe with the help of some young Turks it will be established. But anyway, so the James conjecture, from this point of view, in this type, of course, says that under suitable assumptions, I can just say for now on D block, actually on alpha, on the block and characteristic, that's enough, the reduction modulo P, as explained above, leaves irreducible modules irreducible. You start with a module over this algebra. You choose a lattice over this, an arbitrary lattice, and you just extend scalars to F. You've got a module over this algebra. You have to show that if you started with a reducible module, it's still irreducible in the James region. And James region, roughly speaking, means that P is not too small with respect to this block. And I will tell you the precise condition. And as Meinhof already pointed out, that outside of James region, it's definitely false. Okay. So, there are no further questions so far. I'll move a little bit further. I would also like to point out that so when you study Lie theory, you want to understand maybe not only dimensions of irreducible modules, but a little bit more things like formal characters, things like Weil character formula. And because we are doing the graded representation theory, or because I want to advocate doing graded representation theory, I actually think that the best thing to understand would be the Q characters, so the graded characters. So let me define this thing. And let me state what might be considered the main problem. In the theory, it is to classify irreducible graded HD lambda modules and find their Q characters and describe their Q characters. Yes? What do you mean by the fact that it exists? Yes? Why does the form in the module exist? Well, can't I just take any vector and multiply by this? It will have to be a lattice. Module is irreducible, it will have to be a lattice. Am I missing something? I mean, it won't have any torsion over Z. When you extend scalars, it will have to be the whole module. So it looks like it will have to be a lattice. I mean, you're right in the sense that this is not quite a usual situation for the Brauer-Nesbit induction, because in Brauer-Nesbit you usually have group algebra on top. And so this is a situation where you go from semi-simple algebra to characteristic P. And here you're going from non-semi-simple to non-semi-simple. But I still believe that reduction is defined. I mean, what do you think? Maybe we shouldn't waste time now. Maybe we should discuss it during the questions. Okay, so let me just tell you. I mean, it's an obvious definition. So character Q character of a module M is just the generating function for the graded dimensions of the weight spaces. So this is over I in I to the D, formal sum of Q dimension of the I weight space times I, formal element I. And the Q dimension, of course, is this polynomial, which evaluated at 1 gives you the dimension, but it is a generating function for the degrees. So it's over n and z, Q to the n dimension of the nth graded component when you have a graded vector space. Okay. So this is perhaps the main problem. Now, because this is an introductory, supposed to be introductory talks, I think you will, excuse me if I will go to something rather basic and sort of do classical representation theory of symmetric groups. After all, it's very easy to do it from this point of view. And that might be another thing where I might advertise this, that might advertise this presentation for you. So let me show you a model for the solution of this problem. Of course, it's not going to be that easy always, but let's just concentrate on the case where I have symmetric group and characteristic 0. Okay, so this is a special case of this, so we should be able to do this. Okay, it's a classical theory. And so let me tell you how to do that. So let's specialize drastically. So let's specialize as follows. Let's take f to be of characteristic 0. Actually, you know what? This is, yeah. Let's take f to be of characteristic 0. Let's take psi to be 1, and let's take lambda to be lambda 0. So that's precisely the group algebra of the symmetric group. And, well, we already know secretly what combinatorics is going to come in, so let's not play any games. So there will be partitions and standard tableau. So all we have to do is we have to write down an irreducible module so that you could see its Q character. Okay, and we know that irreducible module corresponding to partition lambda has basis labeled somehow by standard tableau. Okay, can we do it in kind of no sweat way? The answer is absolutely. So let's fix a partition lambda, partition of D, and let's denote by T of lambda the set of all standard lambda tableau. And let's write down the modules. I mean, it's really the case of complete trivialization of classical theory in some sense. So let's write down the modules. To every S or to every lambda, I want to describe a module over the Hecke algebra, over this group algebra. And okay, we already know what is going to happen. Somehow it should have a basis labeled by the standard lambda tableau. So I define the vector space. But now I want to define an action. Okay, let me define an action. And you sort of expect what I'm going to do, right? Because most people studied representation theory of symmetry group. So what kind of thing I'm going to do? There is a name for it. Maybe. There is this Young semi-normal form, or Young orthogonal form, sometimes people call. So you can write down a basis and you can write down the action. But if you have seen this done somewhere, you will see that the formulas which go into the Young orthogonal form are quite unpleasant. For example, you know that you cannot do it over z. You need some square roots. You need to divide by square roots of some strange numbers. And then, honestly, if you want to check it, it's kind of a 5-day job. Something like that. I mean, it's if you want to really honestly check all the relations, and if you have done it, I think it's honest kind of amount. If you are given those formulas, first of all, it's very hard to come up with those formulas. You have to be young to invent those formulas. And secondly, to check them, you still, even if Young gives you these formulas, you have to spend 5 days. Okay. Now here you write down the most obvious thing there is, and it's truly 5-minute job. So it's a very good exercise because we have different relations, because we have different generators. You see, I don't have to tell you how SI acts because it's not one of our generators. We have other generators. So let's guess together maybe how E of I acts. This is going to be the hardest thing. Okay, so it's an idempotent. And somehow, if everything is good, then these guys are probably going to be weight vectors already. We sort of expect this to be a nice thing. And so it should act as a projection to a weight. And the only thing for me is to tell you what weight to associate to the tableau, but it's a well-known thing. So it's going to be the module itself or 0, depending on whether weight is right or not right. And the weight is going to be right is if I is equal to IT and 0 otherwise. So this IT is the weight which we are going to associate to the tableau T. And let me tell you what that is. So IT is I1 ID, where IR is the residue of the box of the Young diagram occupied with R in the tableau T. And again, let me quickly explain that. So here's my Young diagram in the English notation. It consists of boxes, and each box has a residue, which is, if it's in row R and column S, then the residue of the box is S minus R. So if this box, so residue of this box is column number minus row number. Okay, so now I take my tableau, its insertion of numbers from 1 to D into those boxes, and I look where R is. I take this box, I take its residue. This is the Rth component of this. So this is how you read off a weight from a tableau. Is this okay? This is a standard thing, actually, well known. Kind of combinatorics. Okay, so this was the hardest thing. So it just says that those VTs are already weight vectors. And so if you want to know the formal character, you will read it off from the standard tableau by usual combinatorics. Okay. Okay, so now we need to figure out what YR does. Are there any suggestions? if life is really, really, really nice, nilpotent element, 0, and finally psi r Vt. So this is where you expect some horrible square roots and divisions by those square roots on those 2 by 2 matrices. It's V act with permutation SR on tableau T if SRT makes sense, that is standard, 0 otherwise. Okay, so that's it. If you can act, you act. If you can't act, it's 0. So check relations, it's 5-minute work, not a 5-day work. So it's an obvious statement. It's also obvious to check that this is an irreducible module. Or very easy. You should just be able to go from any tableau to any tableau by doing such permutations. It's a very easy combinatorial exercise. And it shows that you span, so you've got irreducible modules. Then to check that you've got all of them, you might use Robinson-Stenstedt to see that d factorial is equal to the square of the sum of the squares. So you can compare that. So again, you can see that this presentation is good for something. It really trivializes the Young orthogonal form, and no, it won't act as 0 on any module, but it will act as 0 in characteristic 0 on any module for this level 1 situation. I'll tell you what this result is saying. It's essentially saying that the Murphy elements act semi-simply. There are no Jordan blocks. Because remember that from Murphy elements, we subtracted the eigenvalues to get y's. And so it's just a statement that the Murphy subalgebra is a semi-simple algebra. So that's kind of a shadow of that fact. Okay. Okay, so I want to show something else to you, which is kind of on the light side also, and maybe I will go a little bit further into the next lecture. I want to stay a little bit in this pleasant situation where I can actually do things by hand, and of course in general you cannot, but I mean this is so nice that you might say, okay, let's try to extract as much as we can from this. Okay, for example, are there any other modules maybe for higher level lambdas for which we can write down explicitly representations. And this is kind of known that you can do it. In fact, the best thing to do it is to work with a fine case. So you take a fine algebra and you're trying to describe all the representations where your commutative subalgebra acts semi-simply. In other words, you're sort of trying to consider all representations where this happens. This is really nice defining property. There are more nice situations where all y's act as 0, and maybe we can do everything by this. And then it turns out that it's not always the case, but there are more nice situations. For example, in type A, what you can handle using this, and again this sort of goes back to Cherednik, what you can handle using this is not just the partition case, but this Q partition shape, this Q shape, partition minus partition. And this case provides such representations for a fine Hecke algebra where yr acts as 0. Okay, so I want to go there a little bit, but even before I do that, I forgot to mention that I promised to do graded representation theory. But in this situation, these representations are all concentrated in 1 degree. So in characteristic 0 for symmetry group on level 1, you're actually really not getting any new information. But in all other cases, you do actually. And basically, another description of these modules where yr act as 0 are precisely representations concentrated in 1 degree. And so let me write this down and tell me what I want to do. Tell you what I want to do. Okay, so what we want is to describe representations where YRs all act as 0. And it's a little theorem to check that this condition is equivalent to the requirement that representation is concentrated in 1 degree. And I think sometimes such graded objects are called pure, when you just have everything concentrated in 1 degree. So I might say all pure representations. So this is really what can be done without too much work. And we are sort of lucky that in the classical situation they're all pure. So that's why symmetric group works. Okay. Now I said describe representations where YRs act as 0 or all pure representations, but representations of what? For what you can do it. And I said that the smoothest way to do it is just to do it for affine case. But in fact, I want to do it for affine Havana-Flauder-Hecke algebras. So this can be done for affine Havana-Flauder-Hecke algebras of any type, or at least of any simply laced type. Could be done for any type, but let me concentrate on simply laced. Not just type A, but for any type. And you can say, what are they? Well, actually, I told you what they are, because my presentation actually didn't depend that much. Okay, you choose any quiver, which is simply laced. You drop the cyclotomic relation, because you want to work with the affine case. And then all the relations were written in terms of the Dynkin diagram. Right? So the fact that the Dynkin diagram was cyclic or linear didn't matter. I can write down such relations for any Dynkin diagram. And so that's what I mean by this Havana-Flauder-Hecke algebra at any simply laced type, gamma. And so this is what we did with Arun. So we did this with Arun Ram. And in type A, what you get familiar combinatorics of skew shapes. But it turns out that you can generalize this combinatorics of partition, standard tableau, skew shapes to any type. And this comes out quite neat. This is without the cyclotomic relation. Yes, you can figure out which of them factors through which cyclotomic quotients, but it's better not to worry about it, because you get a more smooth picture if you just work with the affine case. Okay? And so, and like I said, it's nice because it also shows you how to define Young diagrams and standard tableau for type E8, because there are various such generalizations, but ours works for our situation. Okay, so in order to explain you what the result is, I will just start today and then I will finish next time. But I can already sort of assign you maybe some homework if I will be able to. It's the best to switch actually to the Russian notation for partitions. So there is a famous argument between the English people and the French people, and then Russian people. And so this discussion went on for ages. And I must say that not without trepidation am I entering the fray on the side of the Russians here. Because I think history teaches us that when the French and the English people fight each other, the best thing to do is not to interfere and just stay on the sidelines and enjoy the view. Because if you interfere, the first thing which is going to happen, they're going to join forces and beat you up. After which they will be happy to resume their normal hostilities. But you see, it turns out that for what we are going to do, this is so natural that there was no way to avoid it. So I really didn't want to do it, but I had to, and Arun agreed with me. On which side? On the Russians. Okay, so it's better. Okay, so here's what I want you to think about. And I will explain why Russian notation is so good for what we are going to do. You see, basically, Russians got the gravity right. That's the point. I mean, this is clearly horrible, because if you let it go, everything will fall down. Right? And it looks like French solved the problem, but it only looks like it. Because it will not fall down, but it will concentrate, but it will concentrate in the wrong direction. It should go down along the diagonals. So this is diagonal-centric notation. Okay. I must say that when we wrote the paper and we used this Russian notation, there was some very serious referee. Maybe it's in this. Maybe he's in this room or not. I don't know. But the referee said you should absolutely avoid ethnicity when you write about mathematics. So we had to rename it, and we called it diagonal-centric notation, because it's you know, things will go. I have an idea who it was, by the way. I want. Okay, so what you really have to do is this. You have to consider the A infinity type, because we are. Let's start with A infinity, and then you will be able to do it in any type, and it's so natural to generalize. And then you consider sort of an abacus. So this is -1, 0, 1, just like before. And so you consider abacus which grows, whose runners grow on those vertices. Okay. And on those runners, you are going to place beads. And the beads are going to have peculiar shape, which is actually important. The shape of the bead on each runner, in this case, will look like this. You go up, I don't know, by square root of 2 or whatever, so that you have a triangle here. You have a right, whatever, equilateral triangle with hypotenuse on the runner. And you go this way to every neighboring runner. So in this case, of course, you will get a square, which I didn't draw very well. Okay, and these are the beads. And then what you do is you take those beads and you drop them to the runners, and you let them slide down. This is what is a great thing about this. The gravity is gotten right, so they will slide down, and this is what should happen. And you get bead configuration. Of course, special types of these bead configurations you might recognize. This is partition 2-1 in the Russian notation. Okay, but what is going to happen actually eventually, and I will show it next time, is that what you can do now, you can start with any Dynkin diagram, for example, D4, and you can put runners up, and on each runner you will have a bead, and the bead will have a form, will have a shape exactly like this. So it has hypotenuse on the runner, and then it will have triangles going to all neighbors. For example, in D4, if you're in central neighbor, there will be 3 leaves. There's 3 triangles. This will be the shape of the runner on the main, and then on others there will be just 1 triangle going inside. Okay, and for type E8, for any type, you do the same thing, and then you build these configurations out of such runners, and this is what combinatorics looks like. I guess I still have a little bit of time, maybe just a couple of minutes, so I can tell you a little bit more, because of course not all such configurations work. In particular, in this case, we should be able to get only partitions or skew shapes, skew partitions. And so, and then you might ask, what is a partition for type E8? What's the condition? Or what is a skew shape for type E8? Right? Here we know what it is because we know that it should look like this. And it turns out that the right condition is as follows. So we will define skew shape by the following condition, that whenever I have 2 beads on the same runner, they don't have to be of this shape necessarily, but since we're in this type, I might say as well. So whenever we have 2 beads on the same runner, in between, on the neighboring runners, there should be at least 2 beads. Okay, there could be 2 on one neighboring runner, and there could be 1 here and 1 there. Okay, so whenever I have that, it follows that there are at least 2 beads in between on neighboring runners. Okay, so I guess the exercise is that this is the same as a skew shape in the Russian notation, in this diagonal-centric notation. But this has advantage that you can do it for any type, of course. You use exactly the same thing. Okay, so I think I'll just stop here, and then I will do it in general next time.